This is actually the UN designated week of World Space Week. That's the phrase.
It is indeed.
It is indeed, yes. This is the talk, the known and unknowns of rocket launch, safety and reliability assessment. Skyrora is a UK launch vehicle provider aiming to support the government plans for the space sector growth. Skyrora's strategy is to take incremental step-by-step approach to allow for critical testing and de-risking of the project. The development I've developed 4 suborbital rockets in order to perform real-time testing of the avionics, ground control systems, payload deployment, recovery systems for the vehicles, while developing their orbital rocket for launch from the UK. Skyrora and Strathclyde University have been collaborating on building reliable tools for trajectory and safety analysis, and this project provides an opportunity with direct benefits for all sides and the sector at large. Alan and Christy will describe the plans for the project. Now, Alan is Head of Government Affairs at Skyrora. His responsibility is for managing and engaging with all key stakeholders across industry and government. This includes Skyrora's involvement in the Parliamentary Space Committee, industry associations such as UK Space, Scottish Space Leadership Council and others, and direct engagement with all government authorities, including the space flight regulators, UKSA and the CAA. Alan's background is in international trade and development, and it gives him a new perspective of the space industry developing in the UK. In particular, ambition to change the current economic paradigm and shift that into the new space economy it will necessitate. Now, Dr. Christy Maddock is an expert in mathematical modelling and system design operations. I'm reading this because this is a cracker. Trans-atmospheric flight vehicles, including spaceplane-based launch systems. This is proper rocket science. Dr. Maddock received her undergraduate honours degree in 2002 in aerospace engineering at Carleton University in Canada. Her thesis was on the design of an optical intersatellite link for a LEO-GEO data relay satellite system. Her doctoral research was conducted at the University of Glasgow on the dynamics, navigation and control of the spacecraft formation of solar concentrators in the proximity of an asteroid. I love it when people's careers are far more impressive than mine. Alan, over to you. What more can I say?
Thank you very much, Paul. Good evening, ladies and gentlemen, and thank you very much for the invitation to join you this evening. I think indeed the excitement that the space industry is representing, and indeed it being the International Space Week, I think it's very appropriate for us to be able to have this chance to share with you a brief overview of what the space industry is doing in Scotland, and hopefully maybe give you some inspiration about how we can also encourage the BCS to move towards supporting some of the innovation and the development that's taking place. So we're very grateful to you for this opportunity. Thank you. I think I should note that I think the excuse came up when Skyrora announced, I think it was the creation of 170 jobs in Fife, and I think the news came through the BCS filters, and it was suggested that perhaps it might be an interesting thing to talk about. So I'm very grateful that the news filtered through that way. And yes, indeed, we did make not that long ago an announcement about the creation of new jobs. But to give you the greater detail, I thought it would be interesting to share an overview together with Christy, partly because we're both working together on a project focused around launch, and indeed what's happening in Scotland on launch today is I think really quite exciting. The excuse that Skyrora has to exist, we're a 3-year-old company, we're still quite young and quite new, but we've got a big ambition and quite a big appetite. And this is the excuse that we've given ourselves to exist, particularly through in Glasgow. There are a large number of small satellites being manufactured. In fact, the UK in general has a 25-year-old satellite manufacturing sector, which is very mature and indeed in certain areas world leading. particularly a company called Surrey Satellites. And the ambition that Skyrora has is to be able to help to address the small satellite market, so the companies such as SSTL, such as Clyde, Alba Orbital, Clyde Space, and Spire, who are based in Glasgow, and to help them deliver their satellites into orbit. This is the market excuse that we've got. We are, or had been indeed before COVID, been seeing a positive trend towards the creation of more and more satellites. I think everyone knows that also they're getting smaller in size and more flexible and more agile in their mission types. And mostly today, in spite of COVID, I believe there's a very positive trend around the creation and manufacture of more satellites. We are expecting at least another 15,000 satellites to come online all the way through to 2030. And at the moment, these satellites that are being manufactured within this sector are being launched mostly from the United States. Some are being launched from Russia or Kazakhstan, Baikonur. There are some still being launched from our European colleagues of the European Space Agency down in French Guiana and other places. But the opportunity that Skyrora is representing is to go to launch from the UK, to come up with a sovereign launch facility in the UK. So yes, our ambition, as I said, in the first instance is to meet the growing demand for small satellites by combining proven technology with modern day innovation, focused on creating a cost-effective response and a reliable launcher, in this instance, form of transport for our satellites to get into orbit. We believe that there is the rideshare model that exists today. So again, our colleagues from Glasgow have to send their, I suppose the closest one is send them to Europe, to the Ariane 6 to be launched. The problem that you have there, or even with SpaceX, that they're coming online with their launch facility, is that you have to obviously wait until they're ready to accommodate you, and trying to fit the smaller satellites into the payload, into the nose cone for it to be deployed again, it represents certain engineering challenges. We also believe that obviously there's an opportunity within price per kilogram, which is where indeed our American colleagues and Elon Musk is very much focused on. Actually, Skyrora believes that we can be flexible enough and agile enough to replace a monetary value with a potential economic, environmental value. So we're looking towards the green economy and trying to think that actually space is the environment, and if we focus on environmental aspects, which we do in certain activities within our company, we can actually protect ourselves from the US market in this way. And I suppose the biggest challenge or opportunity that we're faced with at the moment is the fact that there are no spaceflight regulations. There's no legislation in act today to support spaceflight. The opportunity, therefore, is for us to be able to collaborate as an industry involving the regulators to ensure that the regulations which they are proposing will be enacted in a way that is practical and applicable and will actually enable spaceflight for the purposes that we're intending it. Skyrora as a company was founded and has its headquarters in Edinburgh. We've got a really nice office just opposite from the castle with a good view, but unfortunately, obviously we're all working from home nowadays. We do have also within the confines of Edinburgh, we've got a workshop out at Lone Head, and indeed that's I believe it's not that far away from some of the other I think it's the Turing Institute facility there. So we have it's Edgefield, I think it is, the industrial site that our workshop facility is at. We have an engine test bench that we have also in the vicinity of Edinburgh, probably just across the water, so in Fife. And we have an R&D facility in Bratislava, which is where we've been developing or had developed our prototype for one of our vehicles. And we have an office in Dnipropetrovsk in the east of Ukraine, in Dnipro. And indeed, the company does have, other than just having specific physical presence in Dnipro, part of our company is also from Ukraine. Our founder and CEO, Mr. Volodymyr Levikin, was born in Ukraine. He's actually now a UK national, has been in Edinburgh for the last 12 years and fully naturalized. He's been successful in IT, having spun out and sold a number of IT internet-based gaming things, and most notably he was involved in a company called Cupid that I think you may have heard of, based in Edinburgh. The team that we have here, you can see particularly we have a mix of both UK and a bit of Ukrainian expertise. James Jack Marlowe, JJ Marlowe, is the head of our engineering in the UK. He's actually a PhD in propulsion systems from Kingston, and he, as I said, leads up the tech team that we have in the UK and the work that they're doing. Robin here also has had an extensive experience in small launch in the UK, and indeed is head of launch, and I'll be showing you some of his achievements in a bit further down the presentation. Mr. Pavel Batsula, most notably, was involved in a project called Sea Launch, which was the platform, the mobile platform at sea, which was an international project from which rockets were launched in the late 90s, beginning of the 2000s, and Pavel actually played an integral part in that as an engineer in that project. He's now sort of advisor, consultant, and supporting Skyrora, particularly in the engineering area. And his expertise is one of our main inputs that we had from Ukraine. The idea, as kindly in the introduction, Skyrora has been focusing around the concept of launch and how we as a company can create the journey towards launch. We have decided that the best way to do this was to do this through iterations of small launch, from building up from smaller rockets to larger rockets. And here you can see 3 of the smaller rockets that we have built and made ready for launch. In fact, the rocket on the left-hand side there, you can see Skylark Nano. It's a 1-stage rocket that we've launched actually now 3 times. We did the first launch in a smaller state, a state in Scotland called Kildamore, above the Moray Firth, and that launched for the first time in 2018 in the summer. We did again last summer in 2019, and we again undertook a similar launch of that in Shetland, just quite literally over the summer months this year. I think it was August, no, before August, so it was July. The middle rocket, Skylark Micro, is a 2-stage rocket, which again we designed and built ourselves. This is essentially taking the technologies in the Skylark Nano and making it into two stages, deliberately to again, I suppose this activity of iteration of small launch is the idea around de-risking what we need to do to launch, so we get the hang of the health and safety around what procedures we need in place to launch. And in particular, to demonstrate the telemetry and the equipment that we have on board, that this working and fully functional for us to be able to, again, take the next step, de-risk it, and take the technologies that we've proven to work on to the next step. So Skylark Micro was deliberately a 2-stage vehicle to help us learn or demonstrate with the regulators what 2 stages do when you launch them. Particularly from the point of view of trajectory analysis and where they land. In fact, the story around this rocket is, I would say, grossly over-exaggerated in our opinion, partly because when we first applied to the UK Space Agency and to the Civil Aviation Authority in February 2019 for our license, we weren't expecting it to take 18 months for them to be able to come back to us to be in a position to actually authorize this. I did say earlier on that there are no spaceflight legislation, and for that reason, this has been part of the excuse that we've been given, is that they're doing this for the first time. And indeed, yes, the Civil Aviation Authority has been using this as an excuse to create a process around the authorization of launch, and that's part of the reason why it's been taking so long. However, this vehicle we finally managed to launch actually in Iceland in the mid of August. And there's a little video coming on that about launch a bit further on. The third rocket on the right-hand side, there is a hybrid rocket, which is a rocket. One of the stages is a solid rocket engine, the other is a liquid rocket engine. So that allows us to test the bi-liquid fuel propellant solution that we have for our main orbital vehicle. And we are using the two liquids that we're using is our ECOSENE, a kerosene-based fuel. There's another slide about this later on that I'll explain. But ECOSENE is an ecological version of kerosene, or what we believe it to be. For those of you that might know, it's an equivalent of RP1, which is the rocket grade fuel that they use in the US for launch. And the other liquid that we're using actually is hydrogen peroxide under 300 bar of pressure as the oxidizer. And this is notable because obviously when you produce hydrogen peroxide under 300 bar of pressure and force it through an engine through a catalytic converter, you achieve 600-degree oxygen in the combustion chamber, and this naturally combusts with the kerosene. Why is it notable? It's because obviously it means that we don't need an igniter plug or a spark or anything else to set the engine off. We just need to pressurize it and make it run. The Sky High rocket we're planning to launch hopefully in the back end of this year. We're still waiting for confirmation of the receipt of our application for authorization, but we are optimistic that that will take place. This is again a bit more in perspective of the vehicles that we were, our journey to launch from the small Skylark Nano on the left-hand side all the way through to our Skylark L, which is the next vehicle up, which is an 11.5 meter long vehicle, which prototype of which we've created. And indeed, we undertook a demonstration of this vehicle in May of this year. Again, there's a bit more detail about that further down in the presentation. And the Skyrora XL vehicle, which is going to be our main launch vehicle to orbit. That is a 24 meter long, 3-stage vehicle. So I forgot to say the Skylark L is only one stage, and there is only one engine on the Skylark L. But the Skyrora XL has 9 engines on the main thrust block at the bottom there, 1 engine in the middle, and 1 small engine for the 3rd stage. So that's the set of rockets that Skyrora is focusing on in order to achieve regular launch from the UK. As I said, at the moment we've got to the Skylark L. We've developed a prototype. We're in the process of manufacturing the Skyrora XL, but there are more existential questions that we're trying to use the Skylark L and our experience around them to help resolve, including the suggestions around the legislation and the regulatory consultation that's currently ongoing. And so we are very much trying to demonstrate by doing and engage people around this activity. This is a small video of the launch that we undertook of the Skylark Micro in Iceland in August. So that's part of the fun that we had in August. This is again a bit more detail around that vehicle. As I said, it's a 2-stage vehicle. That was the launch itself taking place. This vehicle was due to go to 26. In fact, it was we had it up at 26 kilometers. As I said, the main idea of the mission from our point of view was to, as you can see here on the left, the key objectives, to raise the TRL level of the components on the vehicle itself, to demonstrate and prove the microelectronics that we have in the nose cone, and there's more detail about that in the next slide, to help us develop the launch procedure and reinforce this within our team and through the practice of this, and hopefully to use this as we said, an influence or an instrument by demonstrating, by sharing with the regulators how launch should happen, but actually help them understand what launch means in terms of what regulations need to be in place to make it happen. This is a bit more of the detail of the micro electronics that we have on board, include the central processing unit. This is basically to help us control and track and monitor the performance of the vehicle. We did also have a couple of GoPros on board, and the more astute of you will have noticed that we didn't have any footage of that GoPro from the camera from the vehicle, partly because this vehicle itself, we viewed this as a development opportunity, and as I said, it's turned into now 18 months of waiting with the CAA to get their permission to launch it, which is partly why we went to Iceland. But so that's kind of over-exaggerated the importance of this vehicle. In actual fact, this vehicle is quite, let's say, it was for us, we were viewing it as an incremental step to verify certain things and to learn from it. And what we actually learned from in this instance was that the GPS signal that we were relying upon in Iceland was not as strong as we were expecting it to be when we launched. And while we saw it, as you could see from the video, taking off and reaching its apogee and then coming back down, we actually failed to track the GPS signal when it hit the water. And for that reason, we didn't unfortunately recover this vehicle from the coastal waters of Iceland. However, we did do it with the full permission of the Icelandic authorities. But anyway, so for that reason, also we don't have any footage to share with you from the GoPros on board the vehicle itself. But we do think that this was a very useful experience. This is the first launch that Iceland's ever had in terms of such a small, I suppose, a two-stage vehicle launch. From our point of view, it gave us, as I said, the experience that we needed to understand what was going wrong and what alterations we need to make, and how, particularly with regards to the GPS signal and the location of this. This actually was the Langanes Peninsula in the northeast corner of Iceland, for those of you who know Iceland well. This is quite a remote place, and I think, as you saw from the video, quite a spectacular place in terms of nature, I suppose, and pristine conditions. So yeah, this is just a reflection of the trajectory and the apogee of the vehicle when it took off, and where the first stage approximately was scheduled to land, and indeed where the second stage landed. As I said, we spent a bit of time in the water, in these waters, trying to find it for I think it was 3 to 5 days afterwards. So we became intimately acquainted with the water. But anyway, so. And this here on the right-hand side of the picture there, you can see the container is our mobile command point. In fact, the rocket itself was transported and all within the container. I think, again, you saw on the video images of our team sat inside with their headphones on. This is actually a Faraday cage as well, and for the purpose of obviously trying to maintain the telemetry with the rocket itself. And we managed to fit all that we required for managing the mission inside that container, as well as for preparing the vehicle for flight. We also did undertake a number of meteorological balloon launches as well at the same time. This was to better understand the weather conditions in which we were going to launch. Indeed, we had some challenges because the winds, and particularly the high altitude winds, were too strong for, I think, 3 of the 4 days that we were there, and therefore delaying us to launch, and we collected this data by using meteorological balloons. So as I said, the idea around the small suite of rockets is to de-risk the approach, and as I said, to take technologies from one to the next to prove that it's working. Once we've proved it's working, we can then install it onto the next one. In particular, where we've got to now with the suborbital vehicle, the Skylark L, we have developed a prototype, and as you can see here, the specific things that we've done in-house. We've developed our own propulsion systems. Again, this will be a slide about the engines that we've got, and our own fuel tanks, our own avionics, and indeed our own ground infrastructure, as you saw with the container there. As it says here, of course, we are benefiting from the fact that we can allow ourselves to make more mistakes on smaller scale projects, which then helps us to identify them and de-risk them for the future. So that's part of obviously the reason why we were taking this approach. In fact, it's been very beneficial the point of view, as I said, of reaching out to the regulator, engaging them, and not just the regulator, well, the broader public and the regulators to get their awareness and understanding of what this activity means. There's a bit more detail around the Skylark L vehicle, which is a one-stage vehicle. It could be two, but the nose cone could detach, but at the moment, because this is a prototype, we've only developed as a one-stage vehicle. It has a one 3-ton engine as its main source of propulsion. Here you can see the fuel tanks, separate fuel tanks, one for the hydrogen peroxide. In actual fact, the fuel combination that we have is from between 6 portions of hydrogen peroxide to 1 portion of kerosene. For that reason, the larger fuel tank obviously is the hydrogen peroxide. This is being pressurized to 300 atmospheres and is then being forced, as I mentioned earlier on, through the engine, combining with the kerosene to produce the 3-ton of thrust. This vehicle can take a payload of up to 100 kilograms, and commonly we would say that it can take that 100 kilograms to approximately 100 kilometers, which is the Kármán line or the edge of space. And indeed, this vehicle, we have developed a prototype, and while we're still waiting for permission and the regulations to launch, we are trying to demonstrate that this equipment is already ready to launch and ready for launch. And for this reason, the next slide demonstrates the roadmap that we've had to the processes that we've had to go through to create this readiness for launch. And indeed, there'll be a very short video quickly on the static fire of that vehicle that we did earlier on this year in May of this year. So as you can see, these constituent parts, there's a 30 kilonewton engine test stand that we've constructed, and where we had to test the engine prior to integrating it into the vehicle. We did a number of tests, not just one. Obviously, I think we've done, including what's known as a hot fire test, which is at least for the full duration of the proposed flight of the vehicle into orbit. So that's approximately 1.5 minutes to 2 minutes. As it says here, of course, the avionics checking the test and how the avionics then get integrated into the vehicle there yourself. You can see the vehicle in our workshop and on the stand. Checking out and I suppose checking our modular launch complex and what we've got in order to be able to effect. Here there's also an image of the rail. This is the rail from which it launches. It actually, this rail can be horizontal and fits onto the back of a truck. Just to give you a better understanding of what that means. Again, you'll see it hopefully shortly in the next short video. And here again, you can see some more pictures: the tank integration, the fuel tank, the pressurization test, etc. So yes, these are the processes. This is an image taken of an aerial image taken of what the static firing test was. So this again is the penultimate thing before you actually go ahead and launch any vehicle, any rocket. And this is what Elon Musk went through. I think it was on the 20th of May before his launch and launching the people into US astronauts into the ISS. So yes, this is effectively demonstrating our launch readiness for this vehicle. And demonstrating here the image that we've got is a completely mobile or modular launch complex. So here you can see the containers that you have here. This effectively the entire infrastructure fitted onto the back of 8 lorries, I suppose TIR lorries. The idea being here that we're trying to challenge the paradigm of what's required for a spaceport in order for a company or a vehicle to be able to launch. And in terms of particularly the environmental pitch that I mentioned slightly a bit earlier on, we do believe that the heavy infrastructure that most people have in their minds when they're talking about a spaceport, that we don't really require this. We think that actually mobile is brilliant because it's cheap and it's non-invasive for the environment. At least we don't need heavy, big bits of infrastructure to enable us to launch. So we have our own launch erector. We have the oxidizer filling station, which again, because it's hydrogen peroxide, is stable at room temperature, so we don't need extra power to keep the liquid oxygen or liquid hydrogen liquid in the liquid state. And indeed, the liquid state is also a big health and safety threat, because obviously it's a combustion threat. The fuel filling station, the helium filling station container, which we're using, is basically to clear the pipes before we put everything through. Hydrogen peroxide storage, the command center, the power station, the mobile workshop, and the cooling system. And indeed, then we have obviously the fire service and security personnel on site. But that's effectively what we're looking at as a company in terms of needs for spaceflight. What is it we require? The one thing that you may have missed here is the command center and the mission command center and the tracking facility for tracking the rocket once it's taken off, the telemetry and the communications with the rocket. But yeah. This is the video of that static firing test that we undertook in May. For us, this was a big milestone, obviously, because this is a verification of our technologies and demonstrating that it all works. We stuck it together. Here you can see the mobile rail that we've got, and there you can see it actually coming out the back of a lorry. What we did here was actually we dug a trench for it to fire into, and we filled the trench. The containers you can see there are of water. Water we're using as a health safety measure, because obviously when hydrogen peroxide spills, you can just water it down with water and it becomes neutral. But yeah, so that demonstrated the fact that the vehicle now is ready for launch. We have successfully managed to test the engine and demonstrate that it will take off. The challenge that we had there was actually holding on to the vehicle so that it didn't take off, because that was at least 3 tons of thrust that was demonstrated there. This is just again a technical understanding of the test fire results from our point of view. The engine post-firing inspection and the launch vehicle post-firing inspection, and indeed the particular things that we set ourselves to learn and what that meant in terms of the density check of the propellant for loading, and indeed the fact that we concluded that the vehicle was ready for flight. This again, just another image of this modular launch complex to try and reassert the fact that the perception of the paradigm, we're actually quite light. We don't need to be too heavy on all of this stuff, and that again, we think it's very important to be able to engage with the environmental lobby around this, and indeed around our fuel stuffs. And there's a mention about the ECOSENE fuel that I mentioned earlier on, a bit later on. But the ECOSENE combined with hydrogen peroxide when we're launching actually combines to deliver up to 45% less harmful carbon emissions compared to liquid hydrogen and liquid oxygen. So we do believe that actually we've got a very useful and very important message to those of us concerned about the environment, that in actual fact a launch or 16 launches, which is what we're planning as an average per year, actually will mean much less in terms of emissions than perhaps a lorry driving around the country on diesel for an entire year. So this again, a couple of words about the propulsion system and an image of the engine that you saw firing there on the test vehicle. That's a 3-ton engine. You can see it there inverted. It's a 3-chamber engine with it's all been 3D printed. It's a Inconel, which is the material that we used. And you can see, so the bottom of the vehicle near JJ's head on the left-hand side is the catalytic converter. Then obviously the next chamber is the combustion chamber, where obviously the fuels are inserted to form the thrust. So yes, we have already produced 4 engines and have had 30 hot fire tests of these engines. And that's the main activity that's been going on in Fife, and that's the activity that we're scaling up, and made that announcement about the creation of those jobs. This again is the test bench where we've been doing that activity. Here again you can see the idea around an engine test bench particularly for launch vehicles is that you try to recreate the setup of the rocket itself. So here you can see on the top picture on the left-hand side, the image there, the larger chamber is the hydrogen peroxide, which again is 6 to 1. So that's the reason that you can't quite see the kerosene chamber here on the right-hand side. But we have them stood vertical so that we can again simulate the pressure. The idea is that we create 300 bar of pressure in here and it forces through. And the engine is hung in the tripod there where actually that firing takes place. This is the first, I think, engine test bench of its kind, at least in the immediate vicinity, and we've been using this as quite a successful demonstration of our activities and how hopefully we're trying to build upon this experience and grow it into a larger facility, perhaps not just for ourselves, but potentially for other rocket manufacturers for Scotland going forward. I didn't mention the top stage of the XL vehicle is a 3.5 kilonewton engine, which is a smaller engine, and in fact that we believe gives us a unique aspect to the ride for our satellite manufacturers when we're going there. But this is just a mention of the fact that we also have tested the 3.5 kilonewton engine at that facility as well. Again, a bit detail about the avionics in the Skylark L, a bit more detail, a bit more, I suppose, outline what we're using them for. So the Skyrora XL, which is the main orbital vehicle that we're looking to manufacture and deliver into orbit. As I said, it's a 3-stage, the main thrust rocket being the model. The 3.5 kilonewton engine is the one at the top, and there'll be a couple of more details about that. And we believe that this is the taxi service to low Earth orbit. Low Earth orbit being obviously orbits of approximately 500 kilometers. That's the most in-demand orbit at the moment. So it's low Earth orbit, but it's also sun-synchronous or polar, what's known as polar orbits, which means that the satellite, rather than geostationary, which are effectively around the equator, what Skyrora is targeting in terms of which orbits we're targeting polar and sun-synchronous. So basically the other way around, rather than horizontally, but actually from pole to pole. We believe that because Scotland is located in the Northern Hemisphere and there aren't too many countries further north of us, when we're launching, we have a unique niche opportunity for that. Obviously, that throws us into potential competition with Norway and Sweden and the Faroe Islands and Iceland. But that's the reason why we went to Iceland, is to demonstrate that we could continue launching with them, but anyway, so we'll see. In terms of current progress, so this vehicle is currently under manufacturing. As I said, there are 3 stages. You can see a bit more of the engines and where they're located here. The 7-ton engine, or 70 kilonewton engine, we have now manufactured. Essentially, it's the same chassis as the 3-ton engine, but it's just they've all have turbo pumps attached to them in order to produce 70 kilonewtons. We are yet to do a 70 kilonewton engine test. We hope that will happen again in the latter part of this year, at least before the end of the year, and we have that ambition for our engine test bench to undertake that. The 3rd stage, which is the nose cone or the payload unit, which we are very much spending more time on evolving ideas around, not just the basic structure that you can see here, but the 3rd stage itself, where you can see the arrow. This is also what's being created as a kick stage. So that's the 3.5 kilonewton engine that we've tested, and that actually allows us to, here you can see a bit more detail of the 3.5 kilonewton engine. This is what gives us our unique selling point, which is our taxi service. This means this engine can start and stop up to 5 times, or maybe even more, depending on the speed with which we want to achieve the displacement of the deployment of the satellite. So what effectively this 3rd stage allows us to do is to get to a specific bespoke orbit for the satellites themselves. So we could go to 454 kilometer orbit, for example, for any specific satellite and deploy. And this is again, as I said, our USP in comparison to Elon Musk's SpaceX version, which is the bus, where they're going for quantity and as many people on board as possible, but you basically get kicked off where the bus stop is, where they determine that bus stop to be, which is why we're, as I said, positioning ourselves more as the taxi service to be much more bespoke in our approach and much more specific. And we believe that, again, combined with certain of the other arguments that we have, believe it or not, although hydrogen peroxide doesn't give as much thrust as liquid oxygen does, in actual fact, because of the thrust at takeoff for a number of satellites, this represents an issue. In fact, you're probably aware up at Edinburgh Observatory in the Higgs Boson Centre, there is what's known as a shaker table for satellites to go through a simulated shake when to withstand the shaking that they undergo when they're taking off. Because of the fuel combination that we have as a company, in actual fact, we don't achieve so much G, therefore the shaking doesn't place so much, therefore the satellites don't need to withstand so much pressure. So that's quite an interesting, unique selling point that sets us aside from some of the others. It's just an overview of our development ambition, and when we're planning to do our 7-ton engine test fire, which is again at the end of this year, beginning of next year, and when eventually we hope to get into regular flight. Here you can see it's the mid 2022. Obviously, as I mentioned already, we are hoping that our Skylark L will launch slightly before then, but again, this is very much dependent upon the regulations and us being able to persuade people that we can get an exception to that, or allow them to buy into our experimental license. So yeah, we believe that actually we've had a lot of fun so far, and we're still continuing to have a lot of fun in spite of current circumstances. We've demonstrated some of the technologies, including, as I said, the creation of the engine, the fuel tanks, the 300 bar fuel tanks that we've manufactured ourselves, and the applicability of these engines, these fuel tanks, also for hydrogen powered transport as well. We have our own in-house oxidizer production and distillation facility. That's the hydrogen peroxide that we buy in from the world-renowned manufacturers of hydrogen peroxide, and then distill them up to the level of concentration that we require and the density. On the business front, we have actually signed 22 letters of intent with small satellite manufacturers who are interested in also being hopefully the first to launch from the United Kingdom. And indeed, amongst those are our colleagues from the Scottish space community, as I mentioned already, Alba Orbital, Clyde Space, and Spire. We believe that we have, again, 3 successful launches to our name. We're hoping that the next launches that we undertake will continue to go off successfully, obviously. We've got 3 production facilities, and we've undertaken, I suppose, the most important thing from our point of view was the vertical fire testing thus far. This just gives a reflection again of some of the collaborations that we've got going on. I think one of the interesting things is, question is who wants to launch from Scotland? Well, there's some of the answers to the questions of who wants to launch from Scotland as an opportunity. We have some people, some clients, potential clients from Singapore, from Poland, from Belgium. We have a relationship with the Dutch, the Netherlands, ISIS, which is their space agency. And so, yes, we have. There's a very interesting breakdown of companies who are interested in trying to make such a launch facility work, particularly function from the north of Scotland. A couple of words about competition. We obviously are not the only doing this in the UK, although I believe worldwide there are not more than 150 small launch companies, or even indeed launch companies. Obviously, we're dominated, and the big names are in there. Here on the right-hand side is Virgin Orbit, which is probably one that most people will have heard of. Virgin Orbit is actually located at Cornwall, and their product and their solution is to launch a vehicle from the underside of a Boeing 737 aircraft, and so they have therefore also what's being called as a mobile launch solution. So actually they take off from Cornwall airports and then they fly to the range where they plan to launch and let the rocket go, and hopefully it launches. They've demonstrated that is not quite working the way we want it to yet, but we do consider them as one of the most significant competitors for what we're doing. Although I should say that Virgin Orbit are not really engaged in the UK market the way that Skyrora is, so they're not lobbying for the legislation or taking part in the industry effort that's around that at the moment. The biggest current and I suppose very real competitor, you could say, is Electron, and that's Rocket Lab. Why are they real? Because they're doing it. They've now undertaken, I think it's 14 launches. In terms of their safety record, they have had one launch explode on the launch pad, which is their unlucky 13th. and that happened again relatively recently, within the last 3 months, I think it was, over the summer. But they are I suppose the market leader in terms of the size of the small launch solution that we are looking to position ourselves in. So their rocket is actually, I think it's 19 meters long, and they deliver approximately, I think it's 200 or 250 kilograms, sorry, to low Earth orbit. To the similar altitudes that we're looking at. Orbex is the other UK-based competitor that is actually based in Forres, and they have tied themselves to Sutherland Spaceport, and their vehicle is, I think, a one-stage vehicle, or in fact, we don't know that much about it because they're not as public as we are in terms of their engagement with the general society. Although obviously Orbex has been much more successful in obtaining government support and grants for their activity. And so they're one of the main, I suppose, they're part of the Lockheed Martin consortium, which is focused on the Sutherland spaceport solution. So we believe that we have, with our reignitable third stage and the less G-force, we've got a good set of interesting and unique selling points. The eco fuel that I mentioned earlier on, there's again a slide a bit further down about it, and we believe that we have a really quite a good cost-effective solution. This is just to give you a picture of where we've recently got to in terms of our advisor facility and the people we're engaging around to help us influence government. Particularly, obviously, we have we're very proud to have Tim Peake join us at the beginning of the summer, and indeed Lord David Willits, who was a former science minister, who's helping us particularly now, trying to push with the message to central government about the regulations and how that should work. This is the eco-friendly fuel that I mentioned. This is a technology that we've developed in-house to take unrecyclable plastic, and most in particular, this is taking the, I suppose, for want of a better image or thing to have in your head, the wrap that you have around the hay bales in the farmers' fields these days. That is ideal feedstock for the creation of this fuel. So we take unrecyclable plastic, through pyrolysis, we turn it into, effectively turn it back from plastic into oil. And obviously the fractions, we have demonstrated that we've managed to achieve an equivalent of RP1, which is the rocket grade fuel that the US is using. And so we think that we have a useful solution in being able to extract the unrecyclable plastic from the landfill or take it out of the oceans and use this as our feedstock for our fuel. In fact, we're so keen about this solution that actually we're seeking to set up a couple of installations in remote airports to be able to supplement their need for fuel and hopefully provide them with aircraft fuel as well. And we believe that, so here you can see the number of, what was it, there we go, for 16 launches, I think we were looking at 16 launches for a year, we're looking at approximately 5 million tons of, sorry, not 5 million tons, we're looking at, I think it was, sorry, 400, I can't remember the date, 200 tons of unrecyclable plastic, which helps us, which we can use to turn into ECOSENE to fuel those 16 launches. So as I said, this solution has had a number of awards, and we're really quite proud of it. Obviously, the one thing that we're being challenged on is the CO2 emissions during the pyrolysis process, which we're looking to capture and make sure that actually don't get out into the atmosphere. And that's something that we're finalizing with at the moment. As a company, we also spend a lot of time talking to education establishments and universities and schools. As I mentioned earlier on, we do weather balloon launches that we have actually really enjoyed doing with schools. We've done a couple out at Pennycook with Beastlack Primary School. It's a really interesting way to get hands-on experience about what is exactly that we're doing, and we've got some really interesting pictures to share with the community from that. And indeed, this week, because it's being World Space Week, we're very much in line with what we can do to help that push the awareness of space and what it means. This is a slide reflecting our ambition, and I suppose maybe our exciting ambition, if I can say that. We do believe that with the eco-friendly fuel and the non-invasive mobile platform that we have, that we can actually champion the concept of environmental spaceflight. And from that point of view, we're actually collaborating with the Scottish Environmental Protection Agency to try and reach out to them to say, well, you know, how can we perhaps turn spaceflight as a concept into much more of an environmentally led thing, and maybe change the paradigm for industry companies involved in spaceflight to actually look at the environment as the lead regulator for this. And what allows us to say that is obviously we're talking about 3,000 tons of unrecyclable plastic waste, which will help deliver fuel 119 individual missions to LEO, which means that we can deliver 3,500 satellites into low Earth orbit. These satellites mostly will be providing data around environmental management systems, the types of which you can see from GSI or indeed other number of the other data companies that are based in Edinburgh, Ecometrica most notably, some of the solutions that they're coming up with environmental management systems based on data from satellites. And for this reason, we believe that actually this will contribute to solving or helping to achieve at least 70% of the UN Sustainable Development Goals. We think that we can actually fit 50 PhD students onto our rockets. Now, of course, I meant their experiments or their low Earth, giving them exposure to low Earth orbit for microgravity, and creating 300 jobs within our own company to be able to make the sustainable launch solution within the country. And there's a commitment there to at least 10% of that workforce being apprenticeships from the STEM side. I should say that we do actually have today an apprentice from Heriot-Watt University, so we're one of the few companies in the country to have a rocket engineer apprentice. And then the financials that we're looking towards. So we believe that actually what we're doing is not just launching things into orbit, but actually we are helping sort of land and create a new manufacturing capability in Scotland. We do believe that we are, with the environmental aspect that we've mentioned, that we can actually help to change that paradigm around the environment and putting the environment first. And actually, we do believe that we can stimulate a lot of innovative and tech solutions to help things, help society grow, help give opportunity for new companies, for new startups, creating a new space age. Just to give you a couple of words about the Scottish Space Leadership Council and what Space in Scotland's doing, just a quick reflection. There are now 133 companies, I believe, associated with Space in Scotland, and I mentioned some of them already. We have all representatives of the space value chain, so that's data companies, as I mentioned, which we consider downstream, the launch industry, the spaceports, the Sutherland project, Shetland, and Spaceport 1, and indeed the horizontal spaceports, Prestwick, Machrihanish, who are looking to again compete with or try to get into solutions such as the Virgin Orbit solution. And the upstream, the manufacturing side of things, and so we have a really useful collaboration, I think, throughout the Scottish Space Leadership Council, which is this industry association, which we've also encouraged Christy to take part in. And as I mentioned specifically, we're mostly focused right now on helping enable the regulations, the spaceflight regulations that we require to be able to have effective launch. And on the specifics of the detail, obviously we are sharing with Christy some of the data around the launches that we're doing to be able to help simulate and go into greater detail around the risk assessment of these launches, what the trajectory could be doing and should be doing, and what the risk could be of collision or unexpected explosions or things like this. So we believe that Scotland actually is a unique place to be doing space, and very much encourage everyone listening to reach out and somehow engage. So thank you very much. I'm sorry, I think I've gone over on my time, but I very much welcome questions if it's okay, I think after Christy's presentation.
Okay, I'll change presenter to Christy, and that will enable you to do your bit. Christy, there you go.
Okay. I didn't know if you wanted to pause and ask questions for Alan now, or you want to wait till after mine and then
Should
we can
we take them
still remember.
Should we take them in the end?
I think, yeah, that would be.
Yeah, okay. So. What's the share screen button? So that should be the presentation.
Yes, we see your title slide.
Brilliant. So my name is Christy Maddock. Nice to be talking to you all. So I'm a lecturer, as the bio went, at the University of Strathclyde, and I was originally, my doctorate at Glasgow, and I came over here and got a job as a postdoc and a lecturer, and I've been working in the field of space access, space transportation, and basically anything that flies through the atmosphere up to space or just slightly on the edge of, for about 10 years now. So within the university, Scotland is, as a whole, has a fairly large base of people that are interested in space and that work in space, both from sort of throughout the entire chain. So from academic, so research and development and outreach, right into development of small satellites, CubeSats, through to now, over the past probably 6-7 years, spaceports and launchers and sort of all the related technologies and everything goes along with it. So within Strathclyde, which tends to be a more technically focused university, one of the key strategic themes is, they've lumped together because it on the surface makes sense, so ocean, anything maritime, air, and space. So within my world, which would be, I sit in the research center that is the Aerospace Center of Excellence. Okay, there's a lot of, nobody sits by themselves, nobody works in isolation. And so we pull in from a lot of different fields. So within that, there's mostly in the science, the field, the faculties of science, the faculties of engineering, of which there's about 8 or 9 departments. We work with a number of student groups, both UK-wide student groups, British-wide student groups, and also then things like the Scottish Space School, which we run and link with NASA and ESA. We work a lot with anybody from manufacturing, both manufacturing the vehicle, also manufacturing for crystals, biopharmaceuticals, nanoelectronics, things that could be manufactured in space. We work with theoretical and applied mathematics, statistics, the computational side, so computer science. We work with, say, the fluidics groups, okay, numerical, and also doing more exotic things like how the fuel would work within a fuel pump or to have non-pump systems. Okay, we do sort of, everybody works and pulls in from everybody else. In theory, perfectly happily. In practice, quasi. So this is us, very happy looking team. Well, except for Uranus, who I think is his passport photo, but the rest of us are fairly happy. That's me on the left. So there's about between, I think there's currently 11, and we just hired or are hiring 2 others. So there'll be about 13 academics within the aerospace lab, all within sort of various complementary areas of expertise. So one group would work on slightly maybe more dynamics, some are control, some are aerodynamics, aeroacoustics, some really on the computational side, so mathematicians, scientists, engineers. And if I step back and ask the question, if any of you are academics, you know the answer, but for those that aren't, as academics, what do we do? Okay, so aside from teaching, looking purely at the research side, it's grown more and more from the time of, nostalgically, I did my PhD at University of Glasgow. There's these wonderful things of, this would be where all the lecturers would come and live, and then they talk with their 2 students out in the garden while they're being served tea and beer, and you know, they'd casually walk around and wait for ideas to spring up with no pressure and you know, no urgent deadlines that things have to be due yesterday. So in our world today, we try to, as much as possible, protect the idea that research should be curiosity-led. Okay, so it's driven by what you're curious about, what different ideas you can have, what new thoughts you have. Okay, in practice, it's also driven by who can fund it, if it can be funded, how I can align my curiosity idea with grants and stuff that are available. So I'll look for money. I have to provide my own equipment. I have to provide money to provide any hire research staff or continue paying my research staff. I can hire PhD students. I have to build, if I want to have a lab attached to it, continually fund the lab, upgrade the equipment. Okay, so once I start doing that, my research plan, I get my idea, I canvas it out there. I have to do a certain amount of outreach to say, I get it out, the idea out there, get some feedback at conferences. Yeah. Then once I have my idea, once I have the money, we're off and running. I can't just do it in isolation. Universities are responsible and beholden to society. So a large amount of this is also what can we give back and what is the input of all of our brilliant ideas on day-to-day life, whether it's now, 10 years from now, 20 years from now. So I have to do outreach to the scientific community to get people to use my idea, use my methods, use my code. We have to work closely, or can work closely, with industry. Okay, because more and more industry are drifting towards R&D, and more universities are drifting towards consultancies and methods. And if I have a numerical tool in some degree of how readable is the code, okay, can I get it out there and who can use it? So we'll work with Skyrora because I can use the data they can provide to validate my models and simulations. And then it kind of basically gets us both a little bit forward on what we can do with that development, where we can go next. Okay, then of course I publish, I go back, I put students in, it peters down, and so the cycle continues. So if I talk a little bit just about where what we do in the center. So we do aero and space, and really we do, so part of it is everything from aircraft, civilian, low speed, okay, aircraft. We do a lot more recently on drones, okay, up to anything that flies interplanetary in space. Could we do a CubeSat mission to a moon, to Mars? Could we do a CubeSat mission to Venus, now that they've discovered more interesting facts about Venus? So we've divided into roughly 3 outward-facing labs. One does space, one does AI and computational intelligence tools, and then I sit kind of in the middle. So about 10 years ago, me and another professor, so I did coming from the space side and he was coming from helicopter ground side, we formed a center that wanted to look at space access, anything that flew through the environment and to space, through the atmosphere into space, planetary reentry, partial reentry for reusable launch vehicles. Okay, this is about 2010, so about 4 or 5 years before the UK decided to get into this. Before then, it was Black Arrow in 60s, 70s. Okay, so we run the gambit of a lot of very technical, very specialist. Okay, so we have to be brilliant specialists in certain areas, and then be specialized generalists, you know, understand how it fits into a systems level view. And from my point of view, I tend to look much more at the systems level view, and then within it try to be a specialist in systems analysis, systems dynamics. Okay. So this is just a slide, but the interesting thing is everything we do is funded through grants. Okay, so we can work with a lot of companies, a lot of grant money. The interesting thing, just from a timing wise, coming up to Brexit in December, is if you'll notice, almost majority of our funding is European. Mostly through the European Commission, because they do, and one of the few people that do, blue sky curiosity-led research. Okay, there is some funding from the UK-based research councils, less because they put most of the money into the European-based research councils. And then we have a lot of money from the space agencies. Okay, and then other stuff that are linked, DTC is linked to PhD training centers. So for us, it's a fairly, and everybody, interesting time to see what will happen when we are not part of Europe. So since you're all, to a wide degree or not, computer society, leading from this, how do we do or measure or generate impact? Okay. One of the ways we do it is through open source code. And we use GitHub as our online code repositories. And it's a way to, as a teaching tool, okay, we can post up, so all of the 4th and 5th year projects, we encourage them all to put the code online, to start testing the code, to work with other people, okay? We have, and then 2 for all the researcher-driven codes. So if I develop something in my research, okay, it's not good enough just that it sits on my computer and I understand it and it's got my little cryptic comments in it. I have to actually put work and effort into making it understandable for anybody that comes after me. PhDs are only 3-4 years, and as a manager of a group of PhDs, I need to ensure the longevity of that. So I need to have well commented, well validated, and to a certain degree quality vetted codes. Okay. Within our center, we promote as much as possible a lot of collaborations. Okay, so I have a specialist in aerodynamics who can tell me all about the flow of the wing. I need this if I'm looking at, say, a launcher that has a reentry winged part. So if he's a tool, I can go to our repository, look up where the tool is and use it. And so we have, like most, a public-facing repository for all of our open access codes. And then we have our sort of internal beta testing, may or may not work, or does work, but I haven't commented that well, or, you know, things that this part works, but I need to check something else. Okay, so it runs the full gambit of what development state it's in. Now, these are not meant to be commercial codes. They're not graphic user interfaces. They're not absolutely fancy, fully vetted, fully debugged with a lot of user input. They're code for people who are experts in the field. And they're a link of how to say, I developed something cool as a method. I want to try to then validate, test, get it used and applied as much as possible so I can get feedback on what it does. So most of our center, vast majority of our center is numerical tools. Okay, so we have a design facility. If you've heard of concurrent design facilities, there's about, I think last count was 8 or more all over Europe. ESA use them quite a lot to design missions and design satellites. And it's the idea that if everybody sits in one room or everybody connects virtually, yeah, I want to design a system in real time. So the power person, when they go on and change numbers, it iterates through the entire system because nothing is independent. I can't change the power and not have it change the radiator size, which then changes the entire structure design, which then changes, you know, the orbit and so forth. So we designed 2 so far. One is NeoCore, which was a large ESA sort of foldable small satellite. It was done, the idea what it would do flybys and reconnaissance for asteroids. Okay. The other one was a horizontal launch system that we looked at similar in the sense of similar to Virgin 1, just much more open, but it was, we attached to a, say a DC-10, something like this, okay? And it's attached to the bottom and it would release and go. Okay, same as what Alan was mentioning, the idea that you want to be responsive and mobile and not be, you have to respond on a global level and have a customer base as a global customer base. So the CDF we have is one of the only ones in Scotland, although we're paired with one in Harwell. That's run by ESA and the UK Space Agency. So since you people, well, I'm presuming most of you are not in space and rocket, I'm just going to go back a little bit to say, what is it we do? Why do we do it? Why is it hard? Okay, so a little background on space. The Earth is, okay, I flip between kilometers and miles. Okay, the Earth is 6,760 6378 kilometers in radius, which, since I'm from Canada, to give you some scope, is the exact distance from one coast of Canada to the other. Okay. Leo is about 100, 150 kilometers up to 2000 altitude. Okay. The barrier space isn't actually defined, but roughly it's around between 85 kilometers that the atmosphere drops off enough that I don't have enough density of air particles I can't actually fly. The GPS orbit, since also GNSS is a hot topic, so for Galileo, everything like that, the GPS is about 2100 kilometers out. And the geostationary, which is nice because it means that the satellites orbit at exactly the same rotational velocity as the Earth. So if I put something in geo and it's staring at the UK, it'll stare permanently. It looks like it's permanently above the Earth.
I needed to poo, so it's okay.
You have competition from 7-year-olds. So, just for curiosity, the moon is even farther. If I look at how fast they fly, fairly fast. Okay, the Earth is going about 1,000 miles per hour in terms of velocity. Okay, to get into Leo, getting 100 kilometers up is not hard. Getting 100 kilometers up and going about 7,000 kilometers a second is. Okay, on average, something in Leo, so the things that Skyrora would launch to, okay, at 500, go round in just under 2 hours the entire Earth. This is just a comic I really love, thus promoted at all chances. Okay. If I fired a rifle from one end of the football pitch, okay, the ISS would cross the entire length of the field before the bullet has traveled 10 yards. Okay. The underlying thing is it's hard to get the rocket to the correct velocity. That's what takes all the fuel, that's what takes all the power, and this is why Alan and I are still employed. So if we go back a bit to how do we design, in this case, launch vehicles, but how do we design anything? More and more these days, well, we've always been going, as much as you can use computers, people have tried to use computers. And because they advance at light speeds, all the numerical methods advance at light speed. So a lot of this evolution is taking stuff from theoretical maths and being able to actually put them into practice that are conceivable to be processed by a computer in a certain realistic amount of time. So a large portion of our work is on how to create very efficient, very computationally fast tools that can run on a computer in some prescribed amount of time. So not 3 weeks to get a simulation result, but within a few hours. And then try to balance that against how accurate can I make the models. So we have a lab that looks at intelligent computation. Okay, so we pull in from the common ones, maths, statistics, applied theoretical, computer science in terms of do we use HPCs, do we parallelize the code? And then we have, okay, applications. So we need to pull in all of the systems models, the design models. Okay, so on one side is somewhat application agnostic. The other one is the application side of the models that are methods agnostic. And in truth, you have to work with them together. There's always methods of there's no one method that is good for everything. So just to give you some rough highlights of things we're working on, okay, without going too much detail, but just to give you an idea, because a lot of these will take the tools from one. So say we can take the tools from something we did. If a meteoroid comes into the atmosphere and when it hits the atmosphere, it explodes or fragments, I can track the fragments down, okay? This work generates stuff on the physics of particles. It generates statistical models that if I don't know how it fragments, can I assume a probability distribution of fragments over a certain area, okay? How can I create or write a propagator, something that integrates over, months, years, with the same accuracy as something that integrates over only 10 minutes, 20 seconds. Okay, so we did a lot of work on GOCHE. It was a spacecraft with the European Space Agency that re-entered. Okay. And they had actual re-entry sensors on it and got data from the re-entry. And then they wanted to say, what tools can you develop to predict, not just predict where it will land, okay, and then see how good you are. It's about predicting the uncertainty of the models. I think it'll land within this area, and here's the map of the probability of where it'll land. Okay, this idea comes more and more to design and to all aspects of things. I don't want the single best design for a spacecraft or the single best design for a launcher. I want to evaluate the robustness of my design to minor fluctuations in the atmosphere. How robust it is to wind knocking me off course. Okay. I want to be able to not just plus or minus 10% margin added onto something. I want to calculate that the fact that this is the, say, the wind model, I presume. I can figure out what the uncertainty is, okay, of that wind model. And then I can use that and trace it all the way through my numerical analysis and tell you how that'll impact. If the wind changes, I was wrong by, I don't know, plus or minus 5% and within these bounds and for these input conditions, how does that affect the downrange capability? Is it off by 1 meter? Is it off by 12 kilometers? So we did a lot of stuff with asteroid spacecraft detumbling, fragmenting. Okay, we did stuff with close proximity operations. If I launch a launch vehicle, okay, I have to track every stage, and then once it gets to orbit, I have to also avoid all the existing satellites and things that are orbiting in orbit. I want to look at resiliency, which again is a way of saying I want to measure the uncertainty in something and come up with a design that is robust, that is reliable, or at least that I can have some metrics for understanding how robust or how reliable it is, so I can pick where I want my design to be, which point along the many curves. Whether it's for space exploration, trajectories of planets, whether it's for, I don't know, coming up with rogue planets that escape solar systems from unstable dynamics and go into stable dynamics, or whether it's for launch vehicles and systems. Okay, a lot of the underlying methods we then take and adapt to a lot of the different applications. Okay. This is a cool one, plays a lot on what Alan was saying, what Skyrora is doing in terms of looking at the big picture. I want to look at the entire impact and the life cycle of the vehicle. Okay, so this is a spacecraft, but I look at the entire impact of when I build the spacecraft, when I manufacture it, when I launch it, during the entire operations, when it re-enters. Okay, I look at, I'm not sure if you can zoom on here. Not sure if you can see the zoom, but okay. This is a tool developed by one of the PhDs. Okay, it was his PhD. So if I look at the environmental, he can calculate different, for all the different design phases, things like the economic impact, how much critical raw materials you used, the different types of emissions, air acidification, okay, ozone depletion, how much particulate matter it generated and during every single stage. Okay. I can do social. Okay, how much labor did it cost? How much labor was involved? What was the impact of the health and safety? Okay, the working hours. And I developed these tools so that I can get it. Wow, sorry about that. So I can get some assessment of the bigger picture. This, I put this in only if you're ever interested in more sort of intelligent computerized design. So I want a smart assistant. I want like a Google, Alexa, whatever to say, design a satellite. So this is what we're working on with ESA. Okay. They have a huge database of all past missions. Okay. So the first thing to do is data processing, look at all the past missions, okay, and then try to draw some conclusions. Or at least if I pan it, it can say, I'm looking for which solar sun trackers they used on these kind of missions, and it'll tell me, okay? If I'm looking at things then slightly off. I want to do a single staged orbit. I want to do a space plane that goes into orbit and lands, which has never flown. Okay. I want this to almost query the entire web, okay, and try to then come up with which related disciplines, which things, work done in other fields can I port in. Okay, this is just one example, but the idea of that is really, can I have an engineering assistant? And it does both human-machine interaction. It can input data from people. Okay, so if I interview someone when they're leaving, I can try to leverage all of that data and then everything we've learned so far. Artificial intelligence, computational intelligence, we can debate the difference between those two, but space environment management is also a large topic. And so in the case of Skyrora, they want to launch 16 times per year, 16 launches per year, more if they can get them. Okay. Some of the large constellations are putting up thousands, up to plans for 10,000 small spacecraft, CubeSats, all over in a sort of constellation grid around the Earth. How do you track them? Okay. There is hundreds of that, actually there's millions of space debris up there. Space debris just means things we can't move, okay, uncooperative, from tiny paint flecks to bits of satellites to upper stages. Okay. I need a fast in the sense of a real-time way for operators to be able to not only say, I'm on here, I have to maneuver off of it, but the effect of that maneuver is going to do what 5 orbits from now. Okay. In a 2-year-long scope, if I look at the larger picture, can I plan the best course to maneuver along all the possible debris and the fact that all this debris, everybody else is moving at the same time, okay, for the next 2 years. So you come up with an almost infinite route of trying to track what the best course is over large and small timescales. Plus, then there's things like how you account for space weather, okay. This is an interesting thing. I'll just go through quickly because we're almost 8 o'clock. So one of the things that we do because we like it, we hold competitions for ourselves. And so the European Space Agency started this 2005, and they said to all the people doing optimization, which at the time was smaller and now is slightly bigger, but in space optimization, space trajectory optimization, let's hold a competition. It'll be fun. Okay, we self-defined it because we can. It's not that many of us. So they came up with the American Cup of Rocket Science. Pretty sure that was NASA that came up with that. And they said, we're going to have a worldwide competition. We will give you exactly 1 month to solve it. Yep. Apologies, I have to get back my thing. Okay, and we did. Okay. We were in fact first in Europe. This just required trying to solve how to meet a bunch of asteroids as soon as possible and when to launch them. Okay, how many launch vehicles can we launch and how many asteroids can we rendezvous with? Okay. Sorry. All right, this I'm going to skip through. Okay, you can read it on your own, but rocket propulsion started with some desire 400 BC to build a wooden pigeon, of course. The last thing I'm going to talk about is just a little bit about the work that we do on trajectories specifically. Okay, so this is a very complicated launch vehicle trajectory. Okay, it has a carrier aircraft that takes it out to some range, and then it drops some multi-stage vehicle. Okay, maybe I have different engines on board. I have part of a jet engine, then I switch to rocket. Okay, then I either separate stage 1 and stage 2. And then I have some abort scenario that may or may not happen anywhere along this ascent. Okay, or maybe I just have, I want to recover the first stage. So I have to then track and land that first stage. And the second one goes up and it goes into space. Okay. Maybe I want to change my dynamic model then. All right. I can track one part that, again, maybe there's another second stage recovery, or maybe it goes up to an operational orbit of, say, 500, and then the third stage launches and the upper stage goes up after that. Okay. A lot of what we're working on with Skyrora and beyond is to say, I have very efficient tools to model, to optimize, and to optimize many different objectives, many conflicting different objectives. And I want to analyze not just this one ascent, not just the design of the wing. Right? I want to optimize this entire system as a whole so that I can capture all the dependencies of as many design things as I can look at, okay, into one, and hopefully capture then some of the interactions between it. Okay. Just skip to the end. So, in summary, we have a lot of curiosity-led research, many of which is looking at ways to model launch systems, different types of launch systems, really exotic propulsion systems to more practical propulsion systems, more interesting ones using HTP, for example. And we want to drive that research into industry. Okay, and from industry's point of view, they want something validated. And as a numerical software, we can help expand to say, have you considered other design options? Have you considered the impact on looking at cost, on manufacturing, on changing something driven from how it would be manufactured in the design? Okay, we use a lot of numerical analysis, a lot of computational artificial intelligence techniques. We pull from almost any discipline we can in order to adapt it if it's of use to us. Okay. And the idea is it's not anymore just technical objectives. We start to include cost and development, impact on the environment, the full life cycle, all into the design process. So that's it for me. Thank you very much.